I'm recording. All right. So tonight is unit 8. So that is the new material I'll be presenting. That is the last unit on test 2. But we will have unit 9 before we have test 2. So let's just map out the rest of the semester. So here on October 27th, we are having unit 8. Next November 3rd, we will have unit 9, which will not be on the test. On the 10th, we will have the test, which will cover units 5, 6, 7, and 8. On 17th, we will have unit 10. That's also the night, and out in the lobby is the information technology leadership event. So I'm going to look and see how much I can shorten what I do that night so that you and I can participate somewhat in the event. So, I mean, I have all the lectures are already pre-recorded, so maybe I'll only do questions. I don't know. I have to look at the material. The 24th is Thanksgiving. And then the first will be unit 11. The 8th will be unit 12. Unit 12 is no lecture and a single circuit. I'll give that to you like ahead of time. So that's mostly just a day for questions. And then in the evening program, the finals are on the night that you meet. So that would be what 7, 8, and 7 is what 15. So December 15th would be test 3 on units 9 through 12. So that's what's coming up. So again, tonight, unit 8. Tonight, unit 8. Next week, unit 9. On the 10th, test 2 on units 5, 6, 7, and 8. 17th would be unit 10, but it's also the information technology leadership. 24th is Thanksgiving. You get a break from me. December 1 will be unit 11. The 8th is unit 12, but that's very abbreviated, single circuit. And then the 15th would be third and last test. There's no homework once you finished all their 9 chapters of that book. So once you finish those 9 chapters, there's no other homework after homework 9. Okay. And all the labs had parts except lab 12, it just has that one single part, that one single circuit. Okay. So that's a sketch of what's coming. The big question mark for me is what to do on the 17th. I have to figure out how abbreviated I can make that, so that you can go out and meet people and eat food in the lobby. If it's in the lobby, I'm not sure it's in the lobby. We'll see. I don't know. All right. Okay, so I'm going to pretend you asked me some questions to start, and then you can ask me some other questions. Okay, so what am I pretending you asked me? I'm gonna, oh, that came up first. I'll pretend somebody did ask me about CRC, and I didn't have the CRC circuit up, and I just talked about some other similar circuit that had memory and had edge triggering. But let me do it with the actual sort of circuit showing here. And where was that?
Which circuit is this reference to, or what is this homework, or is this
Homework is summarizing chapters of a book, so no.
Oh, yeah, fair enough. I'm sorry, labs. I meant to say labs. Forgive me.
It's lab 7 because it's related to shift registers.
Perfect. Thank you.
So first part of 7, no, the last part of 7 is floating point number, so it's not 7C. It must be 7, either A or B. Say B, 7B. There it is, 7B. Okay. So the last bit of lab 7B is the CRC circuit. So you get these latches or flip-flops. They have a data and a clock. If it's called clock, that means that it's edge triggered. That means you have to go through one of the edges of the clock in order for something to happen. And let's see if I can give you at least the first. First one here. So I'm going to read in this data 11. I'll try to read it, even though it's got a bunch of zeros. Okay. So I'm going to turn it on. And then what? It says the first, I'm going to read it in normal reading from left to right. I'm not sure that completely makes sense, but that's what I'm doing anyway. I'm going to read the data in our normal reading order and take that as what's coming into D here. So D is first high. That first bit is a high, and I go through a clock cycle back and forth. It remains high, and so the data remains high, and I go through another clock cycle. Then the data is low for 1, 2, 3, 4, 5 clock cycles in this case. So the data goes low, and then I'm going through 5 clock cycles. 1, 2, 3, 4, 5. Then the data was high at a clock cycle. Data high, clock cycle, data low, clock cycle, data high, clock cycle, data low, clock cycle. So that's how this game is played. You build the circuit. The thing that is easy to get wrong is to grab an excluded NOR instead of an excluded OR, because it comes up alphabetically first. So that's the one thing to be careful about when building this, is make sure you grab excluded ORs. And then the purpose of the CRC is to detect errors. So we're imagining that this is the data we want. And so then here I tell you to pick one of the bits, you get to pick which bit and flip it and run through the exercise. And I don't know what you're going to get because I don't know what bit you're going to flip, but you should not get 1010 because that's the answer for the correct data. So it should be a different answer for the different data. Then we discussed that you should really set it up so that the receiver, what the receiver is going to look for is a 0. And so I take my original data and I put 4 zeros on the end and I see what I get. And then I take the original data and put that on the end. So add the output of part C, whatever you got for C, to the end of A. And so you're running something in, And that answer should be, so this answer D, I'm telling you what it should be. I hope you'll actually do it and confirm, but that's the one that should be 0, 0, 0, 0. So you're sending the proper data and you're setting it up. This is the process in C. That's the process you do to get the answer, to get the user to have an answer of 0, 0, 0, 0. So if the data part, so if you do C right, then the answer of D should be zeros. And now I'm asking you to change not one bit as in B, but 2 consecutive bits. So this is what's known as burst error, that the bits that are wrong are together. And so take 2 consecutive bits and flip them. So you could make 2 zeros, ones, or 2 ones, zeros, or a 0, 1 into a 1, 0, what have you. So change 2 consecutive bits, and you should not get 0, 0, 0, 0. I don't know what you'll get here, but it shouldn't be zeros. But what you should get here is zeros. Everybody should get the same thing here, but I don't remember what it is. And people will get different things here depending on which bit they flipped. Okay. On the test, which is on the 10th, I will give you one of these, and so if you've done this the 5 times you're supposed to, you'll figure out how the circuit runs, and it'll be easy, just try to be a little bit careful, but some easy bit flipping and get some points. Okay. Any questions on that question you didn't ask? Okay, no, he has no questions. Okay. What other question did you not ask? An RC demo. So this is not one of the problems. This is like one of the problems. So I think, what is it? The end of 6 and the beginning of 7 are RC circuits. If I ask something twice, you're going to see it again. This is going to be the first problem on the test. And it's the one that's like the first problem on the previous test. This is the problem because it's got a lot of steps and you got to simulate it and do some calculating. This is the one that is going to be of the order of like 20 points when we're done. So not the one to be skipped. Okay. Let's see, RC still on. It is. Turn it off so I can turn this one on. Okay, so this is an RC circuit, some combination of resistors and capacitors. And let's do the simulation part, and then we'll do the theory part. Okay, so I have an oscilloscope. There are 2 oscilloscopes. This is the one I like. There's one that I don't like that looks like that. If you make it work, that's fine. But if it doesn't work, and you call me over or something like that, I'm going to make you use this one because this is the one I like. Okay. So I'm going to put the switch down. I'm going to open up the oscilloscope by just saying going to its properties. And that's too big. Okay. So how am I going to operate this? I am going to turn the circuit on. I'm going to click into the workspace so that it is active. I'm going to hit the space bar to connect the battery to the capacitors. And then I'm going to hit the space bar to disconnect the battery. So it should start to charge, and you will see the oscilloscope, the voltage on the oscilloscope go up. And then when I hit the space bar again, you'll see the voltage across the capacitors go back down. And then I'm going to turn it off. I want to do this relatively quickly. If you get too much data, then the interesting part of the data will be lost. So you don't want to be too fast and it doesn't charge, that you don't get a chance to charge, but you don't want to be so slow that you have lots of data that's uninteresting, because it will only keep so much data. So I'm going to, again, hit the simulate button, click in the space bar, turn off the simulation. On on, space, off, okay. There is the down, there is the up. This controls the time base, that controls the X. And if you get over here, you get a little up down arrow if you click in there, and you can stretch things out or scrunch things up. Okay, this other scale over here is the Y-axis. You can squish it down or expand it. Okay, so we play the game. I put number 1 at what I call the corner. That you can just drag them to get some rough, and then you can get a little more finesse with this these little arrows over here. And so I have this pretty consistently 229 microvolts. So I'm going to look for when it changes and then go back. There, it started to change. So let me go back. So there's my corner. And then I go up to 63% of my saturation voltage. And my saturation voltage in this case should be a 9. It's a 9-volt battery. And so it is 0.63 times 9. I'm looking for it to be 567. So that's what this number 2 should be in its voltage, 567. I'm a little too high right now. So there's 5, 6, and then I can play with these 5, 6, 8. Okay, I'll take that. So there, and then here is the difference between T2. The T's depend on when I flip the switch. That's not interesting. It's how much time goes between that corner and the 63%. That's the time constant. So I'm interested in T2 minus T1. And that it conveniently does that subtraction for me, and I'm getting 10.554 milliseconds. Okay. So what will you do? I will be interested in that. Then I can see that you built the circuit and the oscilloscope. So you will give me the oscilloscope, and you will show me that you know what the hell you're doing with the oscilloscope. So you'll show me with the needles at the 63 at the corner and the 63%. And if you really want to press me, maybe you'll have a little arrow. So I have a snipping tool. Yes. So you would do something like this with your needles in the right position, and you might circle this or something like that. That tells me I know what I'm doing. That you convinced me that you got the simulation answer for the charging circuit. This is the charging answer. So here's my RC practice, and I'm doing it. Determine the simulated charging time, paste the appropriate oscilloscope string. So that is here. There it is. And so then you can either circle it in the picture, or you can just type it out here, but you need somehow to indicate to me, not just that I can have some oscilloscope screen, but I know what to get from that screen. And then let's find, oh, that's the picture, that's not the, and then I need to do the down. So find the corner again. So here I am at 8.999 and see when it changes. Okay, it started to change. I'll go back to the corner. And now going down, I want it to be 37% of the saturation voltage, which was 9. So 0.37 times 9 is 3.33. So I want this to be 3.33. I'm dragging 3.6, 3. I want to get close to 3.33. There we go. Okay. So now here is the discharge time. In the first lab, when we do this in lab 6, they're supposed to be the same. but in general, in principle, general, they're not, and they won't be on the test. Okay, so here is the time for that. So here's my and down here, and that was 13.581 milliseconds. Okay. You need to have a unit, or I'm going to take off a point, so don't forget the unit. Don't lose the easy points. Even if you can't do anything, come in and say a time constant comes in seconds and get the unit point. All right. Now that is the simulation. Any questions on the simulation? Yeah. Okay. So now let's do the theory. So when the space is up, we have the charging circuit. Think of the right word yet. And so let me show the path. Custom, let me make it fatter. There, that's really obnoxious. Okay. So when I'm charging, the battery is part of the circuit. So this is my charging path. It splits, it gets back together, and it does this. So that's my charging path. R2 is not in the charging path. That's what you have to recognize, that they're different. I'm going to have the same capacitors in the charging and the discharging circuit, but I am not going to have the same resistors in the charging and the discharging circuit. So here, so that's the charging. Charge. Okay, so in the charging circuit, R1 and R3 are in series. So for the charging circuit, the effective resistance is 1.21 plus 3.24 is equal to, what is that? 4.45, maybe? I don't know. Kilowatt ohm. Okay, give a unit. What's the equivalent capacitance? I have 3 capacitors. C1 and C2 are in series. Any charge that went onto this one, the top of the 1.6, the plate on the top of 1.6 gets a charge. That opposite charge stays on the bottom plate, but that corresponding positive charge leaves and goes onto the second plate. So these all have the same charge. And that is our definition of series for capacitors. It was current when we talked about resistors. It's charge when we talk about capacitors, but it's the same idea. So if you vision them as, you know, if they were resistors, would they be in series? Then if they're capacitors, they're still in series. That's that. The wiring is the same. Okay, so C1 and C2 are in series, and then that is in parallel. So C1, C2 are in series. Capacitors in series add reciprocally. So where's my handy calculator? Okay, so it's 1.61 on plus 2.41 on equals 1 on. I'm getting 0.96. And that was a microfarad. Let's just try it again to be sure. Clear it out. Get everything clear out of the way. So I have no history. It's completely clear. I'm doing 1.6 1 on plus 2.4 1 on equals 1 on. I'm getting 0.96. Okay. Then the 1, 2 is in parallel with 3. C1, 2 and C3 are in parallel. And capacitors in parallel just add. So that is 1.4 plus 0.96. And so what is that? That is 2.36. Is that right? Can you tell me if I'm wrong? 1.4 plus 0.96, 236. Okay, and that is microfarad. All right, then the time constant, tau, is R times C. And so 4.45 times 2.36. 4.45 times 2.36 is equal to 10.5. And that is in milliseconds. So you just say ms. I had kilo ohms times microfarad. Kilo is 10 to the 3, micro is 10 to the minus 6. When I multiply 10 to the 3 times 10 to the minus 6, I get 10 to the minus 3, which is milli. And then an ohm times a farad gives me a second. So I have milliseconds when I'm done. What did I get simulationally? This was the charging. I got 10.55 milliseconds. And what did I get here? Theoretically, 10.5 milliseconds. So I agree, my theory and my simulation pretty much agree, so that's good. All right. Find the equivalent resistance of the discharging circuit. Okay. So now, where the hell's my circuit? Here's my circuit. I'm going to move the space bar down. I'm going to discharge. You start on the capacitors and move to the opposite plate of the capacitors. So the charge goes like this to the opposite side of the capacitors. That's the discharge circuit. Discharge. Okay. Who's not in the discharge circuit? R3 is not in the discharge circuit. R1 and R2 are in the discharge circuit. Okay. So R1 and R3 are in series and in the discharge circuit. So R1 and R2, what am I saying? R1 and R2. And that is the 3.24 and the 2.55. Why am I adding them like I'm Swedish? I'm not. 3.24 plus 2.55 is 5.79. Now here's the trick for what I give. That is kilo ohm. The capacitance is the same capacitance. So just copy it. That's what I will do on the test. And you will get points, even if you get it wrong. If you get the same wrong answer the second time, or you just say it's the same, you will get that point for saying it's the same or doing the same wrong thing the second time, or if you get it wrong and then you get it right, then I'll give you the points for getting it right the second time. But you don't need to go through the calculation again. You'll get the point even if you did it wrong, but if you say it's the same. But you should have a hint that you're wrong if you don't match the simulation. And then the time constant tau is again still R times C. And that is 5.79 times 2.36. 5.79. 5.79 times 2.36. 13.66 or something milliseconds. Compare that to the discharge, 13.58. So pretty good comparison. That is the game. It's like on test 2, that's like a 20-point game. That's a fifth of the test. There's not as much, there's no backward steps, which some people don't like from the resistor thing. The resistors and the capacitor combinations are not as complicated, but there is the distinction between the charging and the discharging circuit. And there is the problem that the resistors are, what am I saying? The resistors and the capacitors, well, the resistors in the charging and the discharging circuit are different is one thing, and the other thing is that resistors and capacitors combine mathematically in the opposite ways. So resistors in series add, but capacitors in parallel add. Okay. And the simulation part is maybe a little bit more difficult because you have to know what to do with the oscilloscope. All right, so that was the second question you didn't ask. All right, and the third question you didn't ask is for me to go over some floating point numbers, but I'm doing the stuff that I know people usually ask. So I made up some fake ones. All right. So here's some negative 909.093857. Okay, so first thing I do is this one was negative, so I say the sign bit is 1. And then over here, this one down here, the second one where the number was less than 1, the number is positive, so the sign bit is 0. And then down here, when I asked you to go in the opposite direction from what's stored, the sign bit was a 1. And so when I'm putting the pieces together, I know that it's negative of some number times 2 raised to some other number. XXX and YYY, but I know that it's a negative number. This is me telling you when you're running out of time on the test, get the sign points. There's nothing to it. If it starts with a 1, it's negative. If it's positive, it's a 0. If it's negative, it's a 1. Okay. Let's do 909 on the calculator in programmer mode. 909, and here it is. And that used up 10 bits. So the number of bits for the whole number was 10 bits. I imagine I store 23, but I pretend until I store, then I'm working with 24. And so I've used up 10 bits for the whole number. That leaves me with 14 bits down here. And so then I play my game of I have 14 bits for a fraction. And we know that game, like when we had fixed point numbers. I'm going to go to scientific mode. All right. And what was the fraction? 0.093857. Why did I make it so long? Times 2 raised to the, I think it was 14, right? So here's some number. I take the whole number. I don't round, I just truncate. So I'm taking that whole number and I'm taking it over to programmer mode. I'm putting it in here, Control V. And I was expecting 14 and I got, it's telling me right here 12, but I wanted 14 out of it. So I need 2 more zeros out front. All right, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I wanted 14 bits. It gave me 11, so I needed 3 zeros in the front. And that makes sense because the first one is a half and it's less than a half, and the next one is a quarter and it's less than a quarter, and the next one's an eighth and it's less than an eighth. 1/8 is 0.125. I am less than that. Okay, so now I'm thinking of my number altogether as this. With a dot and then this. And my rules of scientific notation or floating point numbers are that this dot has to be moved up here. This dot has got to go there. So I have to move it 9 places. That looks terrible. I don't care. That says places. All right, 9. All right. So the number of shifts I need is 9. It took 10 bits, but I only shipped 9 because of my rule of where the dot goes. And then I have to, what we call bias it. So I'm going to add 127. And so what is that? 136. You're allowed to use a calculator. All right. And so if I put now, so the 136 is my exponent after I bias. So let me go here and put in 136. And there's 100, 1000. So that should be my exponent. 1000, 1000. And my mantissa is this 24-bit thing, except I don't store this leading 1. And so what was left up there? 1, 1, 000, 1, 1, 0, 1, 000, 1, 1, 0, 0, 1. All right. And now I'm going to check it. You can use whatever one you want. This is the one that I've gotten used to. And so signed it was a 1, then it was 1 and a 1. And then down here it was 1 1 0 0 0 1 1 1 0 0 0 1 1, and way down here a 1. And so there is, I hope I got that right, and 908. So it's sort of close to the 909. And let's try it the other way. Let's put in I think you can also play the game this way. So I put in the number and I got for the sign, of course, the 1, for the sign bit 100 100, then for the mantissa 1 1 0 0 1 1 01 000 1 1. Oh, I seem to be off on the end. I seem to be off here somehow on that very last bit. So something I did wrong. Maybe that rounding thing, maybe they round and I truncate or something. So that is the game. That's another game that's definitely on the test. Well, I'll give you one reverse number, and I will give you one number, either the number greater than 0, greater than 1, which I just did, or less than 1. So let's continue playing the game, and then I'll start blathering on about lecture or ask you if you have any questions, but these almost always come up. And again, you just can't use the calculator and write the answer and get all the points. I'm going to ask you for these intermediate steps that you see in the lab, you're also going to see on the test. And so we start off by pretending that I have all 24 bits for the fraction, since there is no whole number. And so when we play that game, we take 0.000568 and multiply it by 2 raised to the 24. And here's the game. Okay. So let's take it 0.00568 times 2 raised to the 24. And that gave me that. And then that I'm going to put into programmer mode and get the binary. And this time, again, there was no. All right. So there was no whole number. And I got, I want 24 when I'm done. That should have been here, up here. I wanted 24, I got 4, 8, 12, I got 14. I got 14, I'm missing 10. Okay, so now I repeat the same game, but instead of doing 24, I do 34. And I should get the same numbers in the front and then just 10 more numbers, if this game is the right game. So 0.000568 times 2 raised to the, and I can use the parentheses and say 24 plus my 10. And now I get this number, 0.000568 times 2 raised to the 24 plus 10 this time. And that's what I want to put in the programmer mode in decimal and get my binary. And that should be 24. That was my goal, to get 24 bits. And there they are. Okay, what did I have in the beginning? I want to copy this. That's what I got from my first go round up here. And remember that this number is less than 1, so it's 0. Or let's just say point. And then I was missing 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then the number. So I converted a number less than 1, so I had no whole number. And this was, and I got my fraction, and that's what I got. So now I want to move this dot part of my game now is to move, not erase, but move this to here. That is my game, to get it, the dot to be after the first non-zero digit. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. When I have a number greater than 1, my shifts are 1 less than the number of bits. And now it's 1 more, but it's the other kind of a shift, the opposite kind of a shift. So this was 11, a negative 11. So here's the gain, minus 11 plus the bias. Let's just say 127 minus 11 is 116. And in binary, there it is. Okay, so there's my exponent, 0, 1, 1, 1, 0, 1, 0, 0, and then what is my mantissa? Up here when I had 24, that leading 1 is not stored. So my mantissa should be 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 0, 1, 0, 1. Let's see how we do. Where is Herr Schmidt? There's Herr Schmidt. And 0 down here was 1, 1, 1, 0, 1. And then for the mantissa, 1, 0, 1, 0, 1, 1, 1, 0, 1, 0, 1, 1, 1, 0, 1, 0, 1, 0, 1. And there's my 5, 6, 7.999. Pretty close to my number. All right. One last version of the game. You're supposed to be asking questions if you have them, but I'm trying to answer the questions you didn't ask me. But if you want clarification, yell out. All right, the final game is the opposite direction. So we know it's a negative number. There's going to be some number times 2 raised to some number. That's what this is all about. Let's get the mantissa is a number between 1 and 2. So I have 23 bits of the mantissa. I must restore the 1. I'm working in the opposite direction now, so I bring back the 1. So I bring back the 1 of this mantissa in the front. Then I divide by 2 to the 23. Because I think about this number. See, thinking about this number. Oh, that was pretty crappy. With a 1 out front. Is there any? That didn't do what I wanted it to do. There are a million ways to paste, but none of them are the way I want. No, they're all worse than that. Okay. So I have this number with a 1 out front, and it's 1 dot, all those numbers. That's what I think I'm storing. Then I can multiply by 2 to the 23 to get it to be, to move that dot all the way to the end. And then to compensate that, I have to divide by 2 to the 23. So if I take this, I'll slap a 1 in front, get this 24-bit number, find what it is in decimal, divide it by 2 to the 23, I should get my number that is more than 1, less than 2. Okay, so I'm in binary mode. I'm putting in the mantissa, I put in my 1 first thing, that was the 1 that is implied. And then I put in my mantissa, 0, 1, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1, 0, 1, 1. And that should be 24. It gives me groups of 4. 1, 2, 3, 4, 5, 6 groups of 4 is 24. And here's my decimal. So I'm taking this. And I'm converting it. Make that little 1 red. And I convert that to decimal, so that's here. And then I'm going to divide that by 2 to the 23. Not question mark it, but divide it. Okay. So that's over in scientific mode. Control V paste, divide by 2 raised to the 23. There it is. As promised, I want a number more than 1, less than 2. What is the exponent? Go back to programmer mode. 000111100. I'm not in binary mode, so that was complete crap. Go to binary mode. I'm putting a binary number in. I should be in binary mode. I'm putting in the exponent 000, which I'm not going to see. 11100. Okay. So there's my number. It is in decimal 28. So 0.0011100 gives me a 28. And then 28, and I have to unbias it. So I subtract 127. Minus 99. And so I put these pieces together. My XXX was at 1.46666. And my YYY is minus 99. Put all the pieces together. Let Google be a calculator. There's my answer. E is calculators and computers use E to represent scientific notation. So that's times 10 to the minus 30. One last time, check with Herr Schmidt. And what am I doing? I'm putting in the number given. Refresh. It was a negative number. It was 000111. And then the mantissa was 01111011110. I made it a pattern to make my life easy. And then there was the result, minus 2.31 times 10 to the minus 30, which is what I got. Okay, don't, what do I want to say? Don't just put it in the calculator. You'll get some points, but you won't get all the points for these intermediate things. I need to see the one, I need to see the 146. I need to see the minus 99. I need to see the steps. I need to see you understand, not just that you know how to use a calculator. All right, that was me blathering on about questions you didn't ask. Are there any questions you want to ask that I didn't ask myself? No. Okay. So now the new material, all right. So semiconductors and diodes. All right. So a lot of our logic circuits are based on semiconductors, and so we want to just understand a little bit. And this is just going to be some vocabulary on the test. So you wanted to do any calculations or anything with semiconductors other than answer some like fill in the blank questions or something, or maybe I'll have a picture and I'll say, well, what am I indicating in this picture or something? Okay, so semiconductors live between conductors and insulators. So electrons move easily through conductors like copper and gold, and you don't get any movement in good insulators like rubber or glass, and semiconductors are sort of in between. They're not good conductors, they're not good insulators, they just live in this in-between world. But they can be manipulated to be better than they were. And that ability to manipulate them is what makes them useful to us. Silicon and germanium are sort of our most common examples, and this has a little bit to do with their chemistry, so they fall in a similar place in the periodic table, just under carbon. So so these are the sort of, this is the vicinity of semiconductor stuff. Okay. So much of our computers today are built of, transistors and chips, and all the things are built out of semiconductors. We did not always build computers out of semiconductors. Back in the 19th century, in the 1800s, there was at least the beginnings of a computer built with just gears. Then in the 30s, and in the 30s they had calculating machines, but not necessarily computers. And then in the 40s they had an actual computer, and it was made up of vacuum tubes, sort of like kind of a fancy light bulb. And the important thing about semiconductors is that they can do what the vacuum tube could do, but much smaller real estate, that they don't use as much energy, they don't take up as much space. And if you see pictures of the ENIAC, which I probably have on the slideshow, the ENIAC can't do what your cell phone does, or even my old 1980s calculator can do. And it took up a room. Where did it take up a room? Where did the ENIAC take up a room? In Philadelphia. It's down at Penn. So you can see it, and it's not just a room, it's a big room. And those people who look like telephone operators, so you don't know what a telephone operator is, but the people who look like telephone operators, they're the computer programmers. Okay. So we get called up on sexist charges, but back in the ENIAC days, the men did the hardware and the women did the software. So women have been in charge of software from the beginning in computing. They were usually math majors. Okay. So back to semiconductors. So the semiconductor can be manipulated. It can be made to be, it will never be as good a conductor as gold, copper, that stuff, but we can make it better. And it's in that manipulation, that changeability, that's where it's useful. And one thing is that what we've studied so far about electronics has been a lot of resistors, and resistors were ohmic. These will not be ohmic, and it will be important that they're not ohmic, that they, this sort of on-off that we sort of exploit has to do with being nonlinear. There's no nice, in a linear graph, there's no nice breaking point of saying, well, here the resistors on and here the resistors off. There's no such thing. It's just, you can have more and more and more voltage. But if you're nonlinear, you can designate a place as on and off. In fact, I will make you do that. Okay. And then we have special semiconductors that can change. So the important part of semiconductors is that we can manipulate them, we can change them. And sometimes it can be the conditions that change them, like the presence of light. So that's all of the semiconductors involved in photocopiers and digital cameras and what have you. They all come from semiconductors whose properties change when they're exposed to light. Okay, so we want to change the semiconductor's property, and you do that by a process known as doping it. And so you take the main semiconductor is some element like silicon or germanium, and then you bring in some other element which is close to it on the periodic table, but not the same as it on the periodic table. So you're introducing some little bit of difference, some impurity, and that's going to give us this difference. So you're usually doping with stuff that's on either side of you on the periodic table. So if you were silicon, you might play with aluminum and phosphorus. If you were germanium, you might play with gallium and arsenic. And so we'll talk about having, extra electrons or too few electrons. And that is this game. Like, as we tend to go across in the periodic table, you have more electrons in your outer shell, if you remember chemistry from way back when. Okay, so even in very, that's 2012, so that's already long ago, 10 years ago, but in semiconductor history, that's pretty recent. And they were finding new things, but they're still playing in that same region of the periodic table. Okay, and the semiconductor was in the middle, and there were so like gallium was on one side and arsenic was on the other side. So you can dope in sort of two different directions. So there's two kinds of doping, p doping and n doping. And so we talk about the electrons in the outer shell, what are known as the valence electrons, and we can have stuff that have sort of quote unquote extra electrons, and we can have things that have too few electrons. And so we can have n doping and p doping. So the material you add is known as the dopant, and some of them have more electrons than your normal semiconductor in the outer shell. Some of them have less. And so that gives you two kinds of doping, a p doping and an n doping. Both kinds of doping increase the conductivity. So we take something that's not a good conductor. It's not as bad as rubber, but it's not a good conductor. And we're going to make it a little bit better. We're going to manipulate it. But either type of doping makes it better, increases the conductivity. I'm telling you right now, I'm being blunt, I'm going to try to trick you on the test into telling me then one of them increases it and one of them decreases it. And if you're listening to me right now and paying attention, you will not be fooled. They both make it increase. Okay. So my brief reminder of chemistry, then I'm going to do an analogy. So if you remember chemistry, good, listen. If you don't remember chemistry, wait for the analogy. And then in the end, this is just some vocabulary that you might find on the test. And if you're worried about it, then ask me what vocabulary might be on the test. Then I'll let you know what things I might ask and what things I probably wouldn't ask. Okay. But if you remember your high school chemistry, then there are this idea of energy levels. So you have the nucleus, and then which is positively charged, and then you have the electrons, the negatively charged, and we like to be neutral when we're done. And when you put the electrons around the nucleus, you put them into these energy levels. And if you remember back again in your high school chemistry or more recently, they were like the S's and the P's and the D's. And so energy is what we call quantized. You can't just have any old energy. An electron can't have just any old energy at once, or at least an electron that is bound to an atom can't have just any energy. It must have these precise energies of, 1s has a particular energy, 2s has a particular energy. So it's allowed to have those energies. It's not allowed to have any other energies. And that's what we mean by quantized. Okay. So now that's an atom. So that was a review of your high school chemistry, because it's been a long time. And now, but we're not going to deal with an atom, we're going to deal with a material, which is a big collection of atoms. And so we're going to bring, you know, a silicon and another silicon and another silicon, and we're going to make, you know, this substrate of silicon. We're going to have a lot of silicon, you know, silicon atom after silicon atom. And when you do that, those energy levels all sort of weirdly combined and shift around and form what's called a band. So I'm a silicon atom, you're a silicon atom, I have my levels and you have the levels, and you have the same levels as I have. But if we get too close to each other, my levels start to affect your levels, and we get these sort of weird combined levels. And maybe your level moves down a little bit and my level moves up a little bit, but they're close together. And then somebody else comes along and they get into the game. And so those levels, those precise levels, sort of form a lot of closely packed levels known as a band. Okay. So let's say we all get together and our 1s's are all affected by each other, and our 2s's are all affected by each other. So there's a set of things near our 1s, and there's a set of things near our 2s, but there's still some space where you can't be. So there are more levels you can be at, because my levels were up a little bit and your levels were down a little bit. So there are more levels you can be, but there's still levels you can't be. And that is the gap. So our levels come together and kind of blur each other out, but there are still places you're not allowed to be. That's the gap. Okay. So here's a picture of the levels of the individual atom, and then you bring a lot of atoms together and those levels sort of band together, but there's still places where there's no energy level. Those are the gaps. What is a question I might ask you on the test vocabulary? I might ask you about bands and gaps. I might show you this picture without the words and say, supply the words, or I might sort of give some description and you put in the word band and you put in the word gap or something. Okay. So you have these bands and gaps, and now we want to, the same way when you had an atom, the electron had to be in those levels. When you have a material, though, the electrons of the material have to be in the levels. And we have the Pauli exclusion principle that says only so many electrons are allowed in a level. So your levels and my levels influence each other, but now the electrons are coming in and they want to fill the levels, and we can only put 2 things in my level and 2 things in your level. Each level only is allowed 2 electrons. Electron has a property called spin, and you're allowed a spin up and a spin down, but that's it. Then the level's full, there's no more room. You have to go to another level. There might be a nearby level, or the next level may be far away. That's part of the question we're going to ask. But if there are 2 electrons in a level, it's full, it's done, next level. Okay. So we imagine this fake process where I'm a silicon nuclei, you're all silicon nuclei, we get together without our electrons. That's absurd, we would never do that. We don't like each other that much. We're all positively charged, we don't like each other, but just imagine this for the process. We're all silicon, we all have our levels, we all get together, and our levels affect each other. And then the electrons come in later, just for the sake of argument. And the first electrons that arrive on the scene, they go into the lowest levels. I said my levels raised a little bit, yours lowered a little bit. So the first 2 electrons would go into your levels because they're the lowest. And then the next two would go to mine because I'm the next lowest. And so that's the electrons would fill up that way. And then when there are enough electrons filled in to make the whole thing neutral, we would have what's called the ground state. That would be the lowest possible energy. Again, all the electrons can't go into the very lowest level because Pauli said so. Pauli said only 2 electrons per level. But we bring in electrons, bring in electrons, bring in electrons, and we bring in as many electrons as there are positive charges. And then if they're all filling the lowest levels they can, given the Pauli exclusion principle, that's what we call the ground state, the lowest possible energy. All right. So we do that. We bring in the electrons, they fill in this lowest level. And now the question is that last level that got filled. There was a first level that got filled, it was yours. There's some last level that got filled, it's probably that guy in the back. He probably got the highest level. Then we said there are bands and there are gaps. And where the last level appears, where the last level occurs, whether it's in a band or whether it's at a gap, that determines everything. So these bands and gaps and the filling of the levels, that determines whether you're semiconducting or not. If we're done filling and we're in the middle of a band, yay, we're a metal. And electrons easily move around and we're a conductor. If we fill the band and we're at the gap, the last band was at the gap, but it's a small gap, we're a semiconductor. And if we fill the band and it's a big gap, we're an insulator. And then there are other things. This is a very simplified picture. You know, we're not material scientists, we're not even chemists, we're just trying to learn a little bit of logic, but all right. It is a physics course. It does have a physics label, so I get to do this at least. I get to torture you with resistors, I get to torture you with capacitors, I get to torture you with semiconductors. It has the name of PHY for a reason, okay. We want a current. We determine whether you're an insulator or a semiconductor or a conductor or an insulator or a semiconductor by can electrons move around. So we had this ground state. If you want to be able to have a current, you need to be able to move electrons into a slightly higher state. We can think of the states as having, it's possible to think of the states as having some of the electrons moving to the left and some of them moving to the right. But the ground state will have as many going to the left and going to the right. So there'll be no net current. If I want a net current, then I need to move some electrons up into slightly higher levels to get more of them going to the right than going to the left, then I get a net current. If I'm a metal, if I'm in the middle of the band, those levels that I want to go to so I can get a current are close by, and it's easy for me to get to them. And so it's easy for me to have a current. If I'm a semiconductor, I'm at a gap, so I have to jump a gap to be, I want to get a little bit excited, but I have to jump a gap, but it's a small gap. So I have to pay a price in energy, but in a conductor, it's almost micro, you know, it's so little of a change in energy. I just do it, it's easy. If it's a semiconductor, it's a little bit hard, but I can do it. If I'm an insulator, it's almost impossible. I can't do it. Okay. That level, when we talked about the ground state and we were filling up, and we said the last level is the important level. Well, it's so important it gets a name. It's called the Fermi level, named after Enrico Fermi. So he was like Italian, but came over to the US and worked at Chicago. So, okay. So The people with important names for this stuff are Pauli. He had the exclusion principles, only 2 electrons per level, and then Fermi. That last level was called Fermi level. And then we want to know, where's the Fermi level? If it's in the band, you're a metal. If it's at the gap, you're either a semiconductor or an insulator, depending on the size of that gap. Okay. The part that we filled, let's say we're a semiconductor. So we filled it up where we're at the gap. And a gap is a space where no energy is allowed. And it's between 2 bands where energies are allowed. So the one we just filled up is known as the valence band, because we had all those valence electrons and they fill that band. So that's the valence band. And then the empty band is the conduction band, because if we want to conduct, we have to move up to the conduction band. So again, we're semiconductors, so our Fermi level came up to filled up a band, and we're at a gap. So we're talking about a gap between 2 bands. The full band below us, below the Fermi level, is conduction band. The empty band above us is the valence band, or sorry, the conduction band. Valence full below, conduction empty above. Okay, so our Fermi level was sort of in this picture here at the gap. Okay, now the analogies. Forget the chemistry, forget the levels. I never liked chemistry anyway. Let's see if we can understand this as an analogy. Okay, we have some university. The university has 100, 200, 300, and 400 level courses. It's not like this place. You might have a 100 level course here that was next to impossible, and a 400 level that you breeze through. No, these are real levels at this university. 100 level courses are easy, 200 not as easy, 300 levels are pretty hard, and 400 levels are just impossible. Okay, so it's not any fake numbering like around here, it's real numbering. It really corresponds to a level of difficulty. Okay. The university, it's a small little place. It offers 10 classes. And the class has a cap of 20 students. Can't go to the chair and smile and say, can you get me in? It's like the English department here. They're not going to let you in. They don't like you. So the chair of English is like Pauli exclusion principle. No, you can't get in. It's impossible. Okay. So we have, we're offering 10 classes at each level, and the classes have 20 students are allowed in a class. So there is an occupancy. There are 10 classes and 20 students allowed in per class. So each level that allows for 200 students. So there are 200 student slots in level 1, 200 student slots in level 2, 200 level, etc. Okay. And there's a change in the difficulty between these levels. That is the gap. You know, think of it as a freshman course. Okay. So now we have we're filling up these classes. So in this small university, we have 100 classes. We have 100 students, and they're each taking 4 classes. And I didn't choose the number 4 arbitrarily. Think about if you know your periodic table, carbon has 4 valence, and the thing underneath it, silicon, has 4 things in it. So, okay. So you take the 100 students take 4 courses. So I need 400 slots for my students. 400 students, 100 students taking 4 courses, 400 students. the 100 level had 200 slots, the 200 level had 200 slots. So when I'm filling them up, the students taking the easiest courses they possibly can take. These students don't want to challenge themselves. They just want a credential. They want the easiest way out. And so they take the 100 level courses and the 200 level courses, and the courses are full. So this is the semiconductor university because it filled at a gap. The 100 level course is filled, the 200 level course is filled, and we are full at the gap. Okay. So the lazy students registered for the easiest courses. The first students who got to register, they signed up for the easiest 100 level courses, and so on and so on. And all the 100 courses filled, all the 200 level courses filled, and the students were done registering. Okay. Now we want to have some conductivity. We want to have some flexibility. Somebody wants to move, somebody wants to change their schedule. So there's some afternoon job, and you want that afternoon job, but right now you have an afternoon class. So can you easily change your schedule to open up for the possibility to take this afternoon job? Is there any flexibility at this semiconductor university? The answer is no. The person in the 100 level course isn't even gonna think about it. I'm not giving up my easy 100 level course. But the people in the 200 level course, even in the hardest 200 level course, you'd have to take a 300 level course to change your schedule to accommodate this job. So it doesn't lead to flexibility. You cannot conduct, you cannot easily move around. For electrons back in the levels, for the electrons to move around, they need to be able to go to the next level, and they need to be able to go to the next level easily if they want to conduct, if they want to be a metal. This is a semiconductor university. We filled up the 100 levels, we filled up the 200 levels. To have any flexibility in your schedule, you got to jump a whole level up. You got to jump over the gap, bite the bullet, take the 300 level course. Okay. Now let's dope. Okay. So I want to bring in something that's close to, but not quite the same as my students. It's something that is a little bit different. Okay. So now I'm going to have some of my students are going to be different. I'm going to have a little bit of doping. I'm going to have an exchange program. I have some students from a foreign country. They want to take, they take 3 courses. So they're learning English, or they want to do some traveling. So they only take 3 courses. Now, all my 200 level courses don't fill. Because before, the exact filling to be at that gap, I had all my 100 levels full, all my 200 levels full. There was no flexibility in the schedule. That was the semiconductor. But now with my exchange program, with my p-doping, I don't fill my 200 levels. And so is there flexibility? Well, for some of the students, there is. They have to take a slightly harder 200 level course. Philosophy 280 instead of English 277. But that gives them the flexibility, and they have the flexibility in their schedule. They can take the afternoon job if there's the p-doping. So that gives you increased flexibility, higher conductivity. P-doping improves the conductivity, at least by our analogy. Let's talk about the other way. Let's talk about n-doping. I have this is a different scenario. Erase the previous scenario, new scenario, new scenario. I have a 3-year program. I have some students who want to finish early. Right? I have some students who want to finish early, so they want to be in the 3-year program. So they take extra courses. They don't take 4 courses, they take 5 courses. Not all my students, just a few of them. These few who want to finish early. So they're taking 5 courses. So when at this university with N-doping, with the 3-year program, when the students register for the class, there are some students in the 300 level classes. Those students in the 3-year program, they might not be the ones taking the 300 level course. I don't know who's taking these 300 level courses, but somebody is. And when the afternoon job opens up and somebody needs flexibility to take the job, that's possible. Those people in the 300 level, there's a slightly more difficult 300 level course that they can take, gives them the flexibility. And doping improves conductivity. Conductivity is about flexibility. Inflexibility is about being at the gap. If you move me below the gap than I was at, you improve me. If you jump me over the gap and start to fill the next gap, you've improved my flexibility. So either doping improves the flexibility. I will try to trick you. Do not fall for it. Both types of doping improve the conductivity. Okay. Doesn't make them good. They're not like gold. They're not like copper. They're not good conductors. They're just better conductors than they were. But I can manipulate them. Okay, so either type of doping increases conductivity. They're not good conductors, they're just better conductors. So that can't be the end of the story. Like, okay, I made silicon nowhere near as good as gold, so what the hell? We're going to do a weird thing. We had the semiconductor. It was not a good conductor. We p-doped it. That made it better. We n-doped it. That made it better. We're going to bring the p and the n together, and we're going to make it bad again. This is known as a pn-junction. So we made it better, and now we made it worse again. Why? Why the hell would we do that? Okay. Let's talk about the analogy for a second, just to talk about this. So we had the P-Dope University with the exchange program. So there were some 200 level courses that were not full. And we had the N-Dope University with the 3-year program, and we had some students up there taking 300 level courses. And students. So they know each other, and so the students in the 300 level course over at in the NU, in the thing with the 3-year program, those students taking the 300 level courses, they know from their friends that there are some slots open in the 200 level course at PU, at the place with the exchange program. And they say, can we take those courses over at the other university and transfer them in? And they go, you have to pay some penalty, but yes, you can take that easier course and transfer it in. And so they do. And so we've lost our flexibility. Yes, they have to pay some transfer fee or something like that. But what's happened? The 200 level courses that were free in the one university have been filled up by the people who were taking the 300 level courses in the other university. And so our flexibility is gone. The flexibility had to be that there were openings in the 200 level courses or people taking the 300 level courses. But when those 300 level course taking students saw the 200 level courses in the other place and they started taking them, we've lost our flexibility. So when we put p dope next to n dope to make a p-n junction, we lose whatever flexibility we gained. Okay. So we say there's, in our analogy, we say there's some penalty. They have to pay a transfer fee, or they have to commute or something. I don't get. In the real thing, in the real materials, let's go back to the real materials. We talked about having maybe extra electrons or not enough electrons or something like that. But everything was always neutral. If you have silicon or you have then you bring in antimony or whatever the hell it was, they were both neutral. So you might have, one of them may have more electrons in the outer shell, but it also had more protons in the nucleus. So it was neutral. But when you have electrons from one side jumping over to the other side to fill in lower levels, you're getting like a charge separation. And charge separations always cost some energy. Think of a capacitor, think of a battery. They have charge separations, and there's energy associated with that. So the penalty in the real world for this jumping over shift to find these lower levels is some charge separation. So that you can do a little bit of it, you can't do a lot of it. But the little bit you do, you lose your flexibility. So we had the pure semiconductor, not a good conductor. We p-doped it better, we n-doped it better, we brought them together, it's bad again. So this is me talking about what I just said, that they were neutral, but now we get some real charge separation. So you had some gain in energy from moving to the lower level, but you paid the price of separating some charge. And so when that gain in energy and loss in energy start to cancel, that's when you stop going over to the other side. Okay, but I have some charge separation. Let's think about this charge separation now. So I have a p-doped and I have an n-doped. So the n-doped had some electrons, then jumped ship over to the p-doped to take those easier courses. So on the p-dope side, there's a net electric charge, negative charge, and on the n-dope side, there's a net positive charge. Okay. So now, why did we do this? We p-doped, we n-doped, we brought them together, we had some gain in flexibility, we lost our flexibility, but we've gained something else. We've gained directionality. Okay, let's connect this p-dope, this p-n junction, this p-dope thing next to this n-dope thing, and I'm connecting it to a battery. And so, I'm going to imagine positive charges moving, because that's the convention we have. Thanks, Ben Franklin, for screwing that up. But that's our convention. So imagine these positive charges coming out of the long end of my battery and coming onto the n-dope side. And the n-dope side already had extra positive charges. And now this battery is bringing along more positive charges, making a bad situation worse. It's bringing in, like, it's increasing the inflexibility. It's making there's this problem with the positive charges and the negative charges separating, and now I'm adding more positive charges to the problem. It does not like this. This does not want to, the electrons, or the charges, I should say, the charges do not want to flow this way. And this is known as the reverse bias direction. This is like the no-go direction. It does not want to conduct in this direction. Turn it around, turn that battery around, send again, by my convention, my positive charges around, and send them to the p-dope side. where I had a sort of extra bit of negative charges. So they're cool with that. Positives like negatives, and so they can sort of get in there and then sort of alleviate the situation a bit. And so they kind of move, they can sort of move through. So they're not making a bad situation worse, they're making a bad situation a little bit better. So they're moving us back to the improved situation. So this is the forward bias, and this is the direction that it likes to flow in. Are we making it into gold? No, we're not making it into a conductor, but we have something that gold never had, direction. One direction we go, one direction we don't go. That's important. Let's think of the analogy of your heart. You've got blood flowing. You want your blood to flow in one direction. You have hearts in your valve to keep the blood flowing in one direction. The currents, the circuits in logic circuits are very directional. They flow like what's in the wall here is AC. That's good for getting it from the power station to us. That's no good for computer circuits. We want DC. We want it to move in one direction. And so what this thing does at this point for us is prevents us from going, allows us to go in one direction and not in the other. It forces a direction. This is going to be used to turn that into that AC in the wall into the DC we need in the computers. We can also use these things to be the logic. This thing is known as a diode, and you can make logic out of diodes. We're going to dress it up more and turn it into a transistor, and that's how we tend to make our logic. But you can make logic. This is already enough to make logic. Okay, so this thing that I've been calling a PN-junction, and that's the proper name for it, because that's what it is. You brought some P dope stuff next to some N dope stuff at a junction, but it's also called a diode. So if you're talking about like what it's made of, you call it a PN-junction. If you're calling about what is the device, then you call the device a diode. PN-junctions are diodes. Not all diodes are PN-junctions, because you could make a diode out of a vacuum tube. A diode just means here's my role in a circuit, whereas a PN-junction is how do I make the device that has that role in the circuit. Okay, I said the valve in the heart. Okay, so when you get to the lab, I'm going to have you do some diodes, and so all this blah blah blah, that's not in the lab. That's vocabulary. That might appear on the test, but what you'll see in the lab is a diode. And a diode has the logical symbol for a diode has sort of like an arrow. So the direction it can flow in is the direction of the arrow, and it can't flow in the opposite one. Okay. So if you further manipulate this situation by making it flow or not flow based on light. And there are two ways light can be involved. In an LED, when you make it flow, it gives off light. So one kind of diode gives off light when it is conducting. We had those 7-segment displays, those displays, and I had you use those used to be made, maybe still be made out of LEDs. You put some current through the diode, it lights up. So that is a diode. A diode is this PN junction. So we went from semiconductors to dopes to PN junctions, call them diodes. There are certain special diodes that are, when they conduct, they emit light, and so they can be used as display. So we can use them for logic, we can also use them for display. sometimes you can play the game in the opposite direction. So that the LED lights up when it's conducting. There's another way to play the game of playing with these materials, and that is that you can become conducting when there's light. That's a photoconductor. So an LED is a diode. If I force electrons through it, if I force it to conduct, it lights up. A photoconductor is something that when there is light, it conducts. And when there's not light, it does not conduct. So they're sort of light's playing the opposite role in those cases. One time it's being used to turn it into a conductor, and the other times it's being given off when it is conducting. Okay, but a photoconductor then becomes a detector. So it detects light, and so anytime we want to make a camera, a photo, a printer, a photocopier, anything like that, even just you put your lights outside your house that light up when somebody walks by, things like that there'll be some beam and the person walks by, breaks the beam, then there's a change in the conductivity, and that is detected. So like it's sort of, it can take a picture, it can be a motion sensor, there are all sorts of things. And it doesn't necessarily have to be visible light. So you might not see it as light, but that doesn't mean it isn't light. Okay. So we'll show how to make some logic out of diodes. We'll show that they play a role in changing AC, alternating current, into direct current. That will be important for us. And they can be used in LEDs for display, and they can be used as detectors. So they can be used to get information into a digital format. They can use to get information out to the world, that they can be display, they can be getting information in, they can be getting information out, they can also be our logic, and they can get the energy from the wall socket into the right format for our computers. So it's a big deal for us. Okay. So the photoconductor is laser printers and scanners and digital cameras and all those sort of fun things that we like. And that is my blah, blah, blah. Let's have a peek at the lab and then see if you have any questions that I didn't already ask myself. What is lab 8A is just more floating points. So I went through that in detail, and the recording, I will post it. So you know how to do that. Nobody asked me questions. So I will hang out so you can ask me more questions. 8B is make a circuit with a diode and change the voltage in C. So this is the voltage across the diode. Here is the current through the diode. So we're going back to like lab 1 when it was a resistor, but now it's a diode. And with the resistor, it was ohmic. This ain't ohmic. Okay. You'll tell me it's not ohmic, but I'm telling you right now it's not ohmic. Okay. And what did we do? We divided the voltage by the current and got the, yes, resistance. So you have to get for me the resistance. I just told you how to get it. You better supply the units or I won't like you anymore. Okay. And you should see that it is not ohmic. Okay. You also, so it's not ohmic, so it's not linear. And you should see, if you were to plot it, you would see like, oh, nothing's going on, something's suddenly going on. It will start to have an on-off kind of behavior. Then in 8P, we move into rectification. We start to see what this directionality does. So I'm putting in this as an oscilloscope. We looked at oscilloscopes in the RC. This is over here a function generator. And we put in something that is alternating current, something that has positive and negative parts. And then the diode turns it into something where you see only positive stuff. So it turns positive, negative stuff into only positive stuff. So we're moving towards DC. And this game is to try to figure out when you're in the positive side, how do I go around the circuit when I'm positive, and how do I go around the circuit when I'm negative? And remember when I had this circuit, when I had this circuit and I was screen capturing it and drawing it, that's what I want you to do here. I want you to draw. Here's the way, at least that I think, the charges move around on one part of the cycle, and here's how I think they move around on the other part of the cycle. So that is 8V, and then quickly 8C. Where are we? Here's just another circuit trying to understand what a diode does. One thing a diode does is gives you a direction. Another thing it can do is sort of protect you from getting too high of a voltage. So it gives you directionality. It gives you changes alternating current to direct current. It can detect things. It can display things. It can protect you from high voltages. And then this is just, you Google something about laser printer, steps of laser printing, and then try to recognize, we just talked about semiconductors and photoconductors. Try to tell me in the steps that you Googled, where's the photoconductor? Okay. So the photoconductor is something that should be reacting to light. The laser printer, the laser is the light. What reacts to the light? All right, so that's what's coming up in 8. I answered my questions in the beginning. Do you have any for me? And then I'll hang out for individual questions, but any questions for the recording? I got nothing. Okay. So I will stop recording.